Even after swinging past the Sun, the interstellar object 3I Atlas refuses to fall silent. The Keck Observatory has captured metals, rare carbon chain molecules, and a puzzling misaligned jet in its outflow. Most molecules expand outward as expected, yet one stubbornly diverges. What exactly is the interstellar object 3I Atlas releasing, and why? The answers in its spectrum are anything but straightforward. On November 16, 2025, the Keck Observatory's Cosmic Web Imager trained its field of view on 3I Atlas, capturing the object's light across a broad slice of the ultraviolet and visible spectrum, from 3,325 to 5,225 angstroms. The instrument, called the Keck Cosmic Web Imager, KCWI, does not just take a single spectrum. It records a full grid of spectra, pixel by pixel, across the area surrounding the nucleus. Every spot in that grid holds a detailed chemical fingerprint, revealing which gases and metals are present and how they are distributed. By using this integral field technique, astronomers could build a true map of the outflowing gases, rather than just a line or a snapshot. These data form the foundation for everything that follows, a complete inventory of the molecules and metals released by 3I Atlas after its closest approach to the Sun. 5 distinct gas fingerprints stand out in Keck Cosmic Web Imager data from 3I Atlas. Cyanogen, CN, appears as a strong signal, tracing active gas release. Iron and nickel are both clearly present, two metals rarely seen together in such abundance around solar system objects. Alongside these, 2 carbon chain molecules, dicarbon, C2, and tricarbon, C3, reveal themselves in the spectral grid. Each of these emissions carries its own story. CN and the carbon chains point to organic chemistry at work, while iron and nickel highlight the release of metals from the surface or from dust grains. The presence of all 5, CN, iron, nickel, C2, and C3, confirms that 3I Atlas is not just shedding dust, but is surrounded by a complex active chemical environment. This inventory forms the basis for understanding how the object is evolving as it moves away from the Sun. The Keck data reveal just how vigorously 3I Atlas is releasing gas, even after its closest approach to the Sun. At the heart of this activity is cyanogen CN, escaping at a rate of 1.6 times 10 to the 26th molecules per second. This is not a subtle trace, it is a torrent of molecules, pointing to ongoing chemical processes near the surface. Alongside cyanogen, dicarbon C2 is detected at roughly 8.8 times 10 to the 25th molecules per second. Tricarbon C3 is present as well, though at a lower rate of 5 times 10 to the 24th molecules per second. These numbers are more than abstract statistics. They measure the living chemistry in the outflow, carbon chains and cyanogens streaming through space and shaping the environment around 3I Atlas. Such strong volatile production rates confirm that the object remains chemically active, with each molecule acting as a messenger from its distant origin. Iron and nickel stand out in the Keck spectra, not as faint traces, but as significant components of the gas flowing away from 3I Atlas. The measured production rates, about 9.6 times 10 to the 25th atoms per second for iron and 6.6 times 10 to the 25th atoms per second for nickel, place these metals on par with the more familiar carbon-based molecules. Their presence in gaseous form, especially after perihelion, signals more than just the release of surface frost. These metals likely originate from dust grains or from the outer layers of the nucleus, where intense sunlight or energetic particles have broken chemical bonds, freeing atoms that would otherwise remain locked in minerals. This is not a common sight in most solar system objects, where metals tend to stay bound in solid form. Here, the detection of both iron and nickel points to a chemically diverse environment, with refractory materials joining the volatile gases in the outflow. The story of 3I Atlas's activity is not just about ices and organics, it is also about metals and the processes that set them free. The post-perihelion observations reveal that the region of gas and dust around 3I Atlas grew dramatically larger than before. Emission scale lengths for key species expanded by a factor of 6 to 7, far beyond what was seen earlier in its journey. For cyanogen, the gas envelope now reaches out to about 6,050 kilometers from the nucleus. Nickel's emission stretches to nearly 3,880 kilometers. This broadening means the activity is no longer tightly clustered near the center, and instead it is distributed across a much wider area. Such expansion hints at processes like grain fragmentation or delayed release, reshaping the outflow's geometry. One detail in the Keck data refuses to fit the pattern. While most gas species, like CN, iron, and nickel, spread outward in the expected anti-solar direction, the emission from tricarbon, called C3, is distinctly misaligned. This off-axis orientation hints at a process confined to a separate region on the surface, a jet emerging at a different angle, or perhaps a unique parent molecule breaking down in a localized patch. The true cause remains uncertain, leaving the chemistry of 3I Atlas with an open question. Why does C3 chart its own path? Every new spectrum from 3I Atlas reshapes what we know about interstellar chemistry. Its unresolved signals remind us that the diversity of the universe is real, and it is not finished surprising us. Share your thoughts below.